Be van kapcsolva igazán.
Okay, it's now my honor continue to chair the last session. Ki van kapcsolva? The last session, okay, thank you. The last session of this great seminar, continuing with the presentation from Dániel Kalmár. Dániel Kalmár, who did his PhD, I don't know, last year or 2 years ago, thank you, at Eötvös Loránd University, a very talented young researcher in seismology, and now he has his own research project supported by NKFIH. Okay, so now we are very glad that we are having you here, and please give you a presentation.
Thank you, Marty, and thank you, István, for the opportunity. I am Dániel Kalmár, and I am working here, physically not here in Budapest, because seismological observatory located in Budapest. So I speak about receiver functionalities in the Pannonian Basin and wider region. This work is not only my credit, because we are working a big team, and this work is framework of the Alpine, and I hope it will be framework of the Adria project. And yeah, this investigation and report funded by national Hungarian government. So yeah, the first question is, what is the receiver function analysis? Receiver function analysis is the best method if you want describe the seismic discontinuity beneath the receiver, so beneath the seismological station and wider region of the seismological station. Of course, this depends on the investigated waveform type. In this example, we show the P2S. I showed the P2S receiver function because we use the P converted wave of the waveform, and after some mathematical calculation, we produce this radial receiver function where the multiplies show information about structure beneath the station. And of course, we can investigate not only the radial receiver function. In the other case, we can investigate the tangential receiver function of the waveforms. The tangential receiver function is the basic situation is flat, because this is based on the deep of the anisotropy of the station, of course, beneath the station. So two familiar methods used during the receiver function analysis. The first is the frequency domain deconvolution. The second one is the most stable and which is show most reliable results. This is the iterative time domain deconvolution, because this depends on one parameter. This one parameter is the iteration number, because this method based on the cross correlation vertical and transversal components of the waveforms. So in all cases, we use iterative time domain deconvolution, because the first part of my presentation, I will present the P2S receiver function analysis, and the second, I will present the S2P receiver function analysis. P2S receiver function analysis, it was the target. The target was the crustal structure determination beneath the Pannonian Basin. We used precise preprocessing steps and rotation and of course the deconvolution, and we used 3 independent interpretation methods. If you can see the details in the Journal Geophysical Research Solidors article 2021. And the S2P receiver function analysis is my postdoc project, and the target is the LAB determination based on the negative phase depth of the receiver function. In this case, we used 2 types of migration, and we submitted the paper in the last month in this study. So first of all, yeah, the study area, the Pannonian Basin, it's a typical background basin. In this case, in the P2S receiver function case, we use 2021 seismological station. We use permanent station Hungary and neighboring countries, and of course we use some temporary project here. Carpathian Basin project station, South Carpathian project station, and of course the Alpine station. For the receiver function analysis, we use teleseismic earthquakes. These earthquakes arrive the epicentral distance of the earthquakes between 28 and 95 degrees. The magnitude larger than 5.5. So in the optimal cases, in the most best cases, we have 70 years data at permanent station. And of course, we have limited data at the temporary station, 3 years data at Alpine and 2 years data CBP and SCP station. We doublet broadband 3 components waveform of these events. We download more than 500,000 waveforms for the analysis. So we have a very big data set. Therefore, we use 3 independent quality control process. The first 2 quality control was applied for the raw Z and E waveforms. The first quality control was the HTLT detector, and the second was the complex signal to noise ratio investigation. After the first 2 quality control process, we rotated the waveforms. These maximize the useful energy for the analysis. And after the last step, we calculated the receiver function with iterative time domain deconvolution with 140 iterations. And the third quality control step was performed on the radial receiver function based on the value and time delay of the dominant amplitudes. So in the left side shows the stacked receiver function from the Dine-Pannonian basin to the Western Carpathians before the quality control. And you can see the B picture after the quality control process. And we can see the P arriving and the PS and the other multipliers also seeing. You can see the Pannonian basin a little bit tricky. This is the effect of the sediments because the PS is observable, but the other multipliers is a little bit tricky. So, yeah, the first interpretation method was the H-VPVS research method, where the H is a Moho depth, the VPVS is a VPVS ratio of the crust. In this case, we set a lot of initial parameters for the each station separately. I show 2 examples. That the first is the MORA station, which is located in hard rock, and you can see the receiver function is very nice if you sort that by epicentral distance. And the other cases, which is located in the Great Hungarian Plain, it's a fixed sediment. The receiver function is not so fine, but we can observe Moho depths and VPVS ratio of the crust. So it was the first estimate of the Moho depths and VPVS ratio of the crust, and these results serve as good starting parameter range of the receiver function inversion. Because the main work of the PhD was the receiver function inversion, where we applied neighborhood algorithm method. This was performed individually for each of 221 stations. The basic idea was the back-azimuthal grouping. We sorted by receiver function by back-azimuth. We bind every 30 degrees. And if the PS and the other multipliers arrive same time, we use only one stack beneath the station, and we used only one stack during the inversion. However, like in example, which is at GLV6 station, which is located in Bohemian Massif, the PS is you can see the radial receiver function here, and the PS is changing, and of course the tangential component is also changing. Therefore, we use 2 different stacks during beneath one station, and we have 2 different results beneath one station. So it was the question, how can you handle this feature of the station, because this station located beneath one place. So therefore, we developed a new visualization algorithm, which called natural neighborhood cone interpolation. This model is not directly CD, but it is constructed by a much larger number of 1D models, time classical interpolation. The basic idea was the cone beneath the station. So you can see the seismological station here, and we have three discontinuity: sediment, Conrad, and Moho. The radius of each discontinuity determined by Fresnel zone and the highest angle of the incident S wave. You can see the mathematical formulation here. And in this case, we can handle the real measured data because these circle was divided by back-azimuthal grouping. And of course, we don't have data from one direction. This circle will be empty. And we, in the left side, shows the piercing point at the Moho Deep. And you can see we have very good resolution in the western part of the research area. And we have a good resolution in the eastern part. But of course, we can improve this area if you add former Pakéz or nowadays Adgare station in the area. And of course, some Romanian station here. So I would like to show some results. This is the basement map from the receiver function analysis, which is correlated very well with previous investigation. The fixed sediment located beneath the Great Hungarian Plain, Vienna Basin, and Drava Basin. And the previous, this is the new thing because the previous map is based on active seismic measurements and borehole data. So we produced the first Conrad discontinuity map of the region, where the thinner part of the Conrad located in the Great Hungarian Plain, the thicker part located in the Orogens. And we produced a new Moho deep map of the region, where the thin part located beneath the Great Hungarian Plain. This map show much reliable and smaller uncertainty than the previous ones, and maybe our results reliable. And we can see the deep of the Moho is 2 times bigger than in the eastern parts than the western parts of the research area. I would like to show some comparison later with previous maps. We produced the first data-driven upper and lower crust thickness map of the region. This is based on the velocity gradient of the upper crust and of the lower crust, because the velocity changing is not so high here. It's the maximum is 0.2 kilometer per secondum. However, the gradient of the upper crust is almost zero and little bit positive. In opposite, lower crust gradient is clearly positive. Therefore, we can produce the upper and lower crust thickness map of the region. The upper crust thickness map shows a thicker value than lower crust thickness map, and this phase 2 maps is a very good initial point of the geodynamic modeling or other geological interpretation. So yeah, the Moho deep comparison with previous studies. So the first map shows Moho map from Grad et al., which based on global receiver function and passive seismic data. The B map shows the Moho map from Horváth et al., which is based on gravity data, active seismic measurements in the Pannonian Basin. And the C map shows our first map from the age VPPS research method, which based on only 2021 data points, and but this show much detailed results than the previous one. And the D map shows our final map from the non-linear inversion with a natural neighborhood cone interpolation. And this map has, I don't know, it's more than 100 data points. So this is the conclusion of the P2S receiver function studies. I highlight the most important. We mapped the thickness of the major crustal layers and determined the ash wave velocity, the top of the bottom. I am not I am not sure the details in the presentation, but you can see details in the article. The core depth, upper and lower Carpathian map are the first for the Pannonian basin, and the Moho depth map present local variation with more finely and better resolved values than previous investigation. And I think the most important take-home message, the eastern part of the area we can improve if you add, for example, the Adria race stations. The present project is the S2P receiver function analysis. In this case, we would like to determine the LAB beneath the Pannonian basin. So in this case, we use more station because some other project is available, like a package, and we got a lot of station from the Romanian colleagues because we are working together in this topic. So it was very helpful for us. We used altogether almost 400 stations. And in this case, also we used the teleseismic earthquakes. And of course, we need a smaller epicentral distance range and little bit lower frequency. In this case, we downloaded same waveform quantity, but the quality was the preprocessing was also important for the good quality receiver function. So therefore, we developed the quality control for the S-wave. It was very important step because we can handle the big data set in this case automatically. After the first quality control step, we rotated the waveforms, and in this case, we maximize and minimize the useful and unuseful energy for the analysis. And after the quality control process, we use the same iterative time domain deconvolution for the S2P receiver function process. And in the last step, we performed the quality control for the calculated S2P receiver function, where the first positive peak shows the Moho, and the first negative peak shows the LAB beneath the station. But this is not a LAB in all cases, therefore I call in the presentation negative phase depth of the receiver functions. So the first interpretation method was the receiver function 1D migration of the receiver function with Jasper 91 global velocity model. This is the example at LTVH station, which is located in the Great Hungarian Plain. So we can see the results here, and maybe Nori will more detail about the 1D migration with local velocity model in the next presentation. So this map shows the estimated depth of the negative phase depth from the 1D migration. So we see the thinner part of the lithosphere located beneath the Great Hungarian Plain, and the thicker part located outside the Hungarian territory. In the second case, we applied the 2D common conversion point migration of the S receiver function. This is the pre-stack migration. So in this case, we don't use stacking of the receiver function because 1D migration, we use only the stack of the quality control receiver functions. And this is the cross-section from the diagonal the Western Carpathian. So in this case, we defined a lot of cross-section and we migrated the receiver function beneath the sections. And you can see the interpreted negative phase depth of the receiver function here. And this is show the piercing point of the orange dot. Calculated piercing point of the quality control receiver function, and it was the fixed point of the interpolation of the last map. And these values show the average negative phase depth of the station based on CCP migration. So this 3 map is a the results. The first, not my results. It is the most familiar and most most famous map of the LAB in the Circumpannonian region, which based on heat flow data, magnetic data, and seismic tomographic data, and our first map, which is based on 1D migration with global velocity model, is almost same, but much more detailed outside of the Hungary. And the C map, which were produced from the results of the CCP migration, is a little bit different than the previous map, because in this case we see the other discontinuity beneath the orogens and the edge of the study area, and I would like to show some cross section which complex interpretation. This section from the Bohemian massive via Pannonian basin of the South Carpathian to the end of the Mysia platform. This is the topography of the section, and this is the heat flow curve of the section. And the second panel shows or migrated results with the negative phase depth interpretation. And the third section is a VP velocity perturbation by Renatal 2020. And we can see we have very good correlation beneath the Pannonian basin where the heat flow is high, but we have not so good correlation beneath the orogens where the heat flow is lower. So maybe we can see the other discontinuities in this part of the section. Yeah, and I would like for some conclusion. Maybe the most important, the precise waveform processing and the Ash receiver function calculation procedure are essential to produce reliable results. We map the thickness of the LAB and maybe the MLD based on the negative phase of the S2P receiver function with minor uncertainty. The average uncertainty of the whole data set is plus minus 5 or 6 kilometers, so it's much smaller than previous one. And I think the most important take home message is the shallowest deep values of the lithosphere are located under the Pannonian basin, where the heat flow is highest. The larger lithosphere thickness located beneath the orogens, where the heat flow is lower. We are not detecting the LAB, but we identify this interface as MLD. Yeah, but a little bit controversial. So, yeah, some acknowledgements, and thank you for your attention.
Thanks, Dani, for keeping the time frame quite well. So you will still have several minutes for your presentation, but the good news is that we have plenty times to discussion.
Thanks for a very interesting presentation. I'm a little bit intrigued by this last sentence in your conclusion. The larger lithospheric thickness can be observed at the periphery of the study area, but however, we are not detecting the lab, but we identify the interface as the mid-lithospheric discontinuity. I mean, how can you then speak about a thicker lithospheric thickness when you cannot find its lower boundary?
The question is good. It not was my idea, because this is the idea of the petrologist in this work. So
yeah, but I mean, this is a little bit strange that you then speak about a larger lithospheric thickness. Okay, that's fine, but then basically, then you speak about that you detect the mid-lithosphere discontinuity. So it suggests to me, if you take that mid-lithosphere literally, that indirectly you can say something about the total thickness of the lithosphere?
Yeah.
Or does it mean there is no asthenosphere at all? In this case, that
Yeah,
because
so-
otherwise I would expect that you can identify the lithosphere-asthenosphere boundary.
Don't if I can answer this.
Okay.
A good question. So I think actually it's just probably as Sierd pointed out very well, it's a wrong wording because it's really not. Of course, if we want to say something about the lithosphere-asthenosphere boundary and the lithospheric thickness, we need to find the LAB. But the problem is not only here in the Pannonian Basin, but also elsewhere in the world. The LAB is identified below this negative phase depth at the mid-lithospheric discontinuity. And especially in this Phanerozoic part of Europe, it's very often sort of puzzling to distinguish the LAB from the MLD. And it's a very common problem. I mean, Karin Fischer and others in North America run into the same trouble. So, I mean, making the distinction between the two. But we are lucky at places like the European platform of Murgia, where, of course, we expect larger lithospheric thickness, but we still see the middle lithospheric discontinuity.
Yeah,
Coming back to that, then basically you say, well, this MLD is basically for you then the lower boundary of the lithosphere, but then I do not understand the term mid-lithosphere discontinuity. Because mid means total lithosphere is basically double so deep as the position as the MLD.
If I understood your word well, then of course, when we say mid-lithospheric discontinuity, we implicitly assume that the LAB is deeper than the mid-lithosphere discontinuity. So basically, what we are saying is in terms of thermal age, we distinguish places like the Pannonian Basin, like the heat flow is high and the processes are young. And in that case, this negative phase boundary coincides very well with the classic lithosphere-asthenosphere boundary. But if we are moving towards colder and older lithospheres like cratons or Proterozoic continental plates, then the lithosphere-asthenosphere boundary, which really isolates the continental lithosphere from the asthenosphere, is deeper than the mid-lithospheric discontinuity. But if we, look at the global images of this negative phase boundary, we very often see that at average, we found this discontinuity around 100 kilometers. The clear exceptions are only old cratons and, of course, young oceanic basins and young lithospheres. And of course, in that common paper with Donny, we are also sort of suggesting this because it's a real controversy. I mean, Rainer Kind also had trouble to identify or to interpret these horizons that he found.
So it means that your lithosphere thickness definition in this case is entirely based on an isotherm of 1200, 1300 degrees or so, but not constrained by seismological observations.
Yeah. Well, I mean, it's constrained by seismological observation, but probably in Nóri's talk, she will begin her talk with a little bit of discussion on how we define the LAB, and we will see how complicated it is.
Donny, would you like to comment on it?
Okay.
Then I move to the next question.
Thanks, it's a very interesting talk. I have a very quick question regarding the Carpathian band. You showed Carpathian band,
okay.
the Branche, and of course the basins, what you showed there. You have a very low geotherm there to show those, and I'm just quite a bit interested in the fact that is it low because of the actively sinking slab, or is it there because we know there have a lithosphere thickness, thickening, besides that part, and is it owed to that? So I mean at where the Branche is, let's say, or in between the Branche and the, what is it, the SC?
Yeah, it's a good question. I think maybe both.
Both, yeah. Okay, thanks.
Because specific, typically is beginning here, and maybe we can seeing here, so I don't know where is the branch exactly, but so yeah, we can see something here. So I don't know exactly what is this in the, and you can see same in the VP velocity perturbation. So yeah.
Okay, sorry, just one again question. So you say that you have this cold, what is it, geothermal bit also towards the Transylvanian basin. So that could also be, let's say, a kind of remnant. Of course.
What?
Okay, a remnant, because you say that they are linked together. You mean, right? This.
Good question. I am not geologist, so okay.
We'll discuss about it.
Okay.
Okay. Thanks.
I am seismologist, so sorry for that.
Great work, congratulations,
Thank
and
you.
I hope you guys can keep measuring, and it's lovely that you work together, the Romanians, because gave you a bigger control area. What very striking for me on this image, among other things, is this LAB disturbance kind of thing, which you show between somewhere between the Bohemian Massif and the Pannonian Basin.
Yes.
So what's the story there? Is it for real? And if it's real, what might be the storyline?
I don't know exactly, but maybe this is effect of the small Carpathians arch.
Okay.
So maybe.
Yeah, I know where the little
So
Carpathians.
maybe,
Yeah,
so maybe we can hear in the small perturbation.
Okay. Because it looks a little bit odd, to have something like that. And yeah, anyhow, it's just an observation.
Yeah.
It's coming on this last cross section. It's coming from the lowermost cross section, and then it is really on the data set. It seems to be something.
Yeah, something
Not very
happening here
clear
because something happening there because it's two different sections. This is the VP velocity perturbation. This is the VF velocity perturbation, and both of them observe this feature.
If I just look at it could be anywhere. It could be anywhere, but it's a. I was wondering whether it's the data resolution issue that or it's for real.
I think this is the real. Yes.
Yeah. Even you can see even an anisotropic picture. So it seems to be something, but you are right.
Okay, but the data is good, I think. Yeah, but I think the data and the data coverage is good in this area. Yeah.
That's what I wanted to hear.
Okay.
Something that is.
Yeah.
Okay, any question? If not, then thank you very much. For this nice and the next speaker will be Nóra Liptai. Nóra Liptai will drive us back to a kind of mixture of geophysics and geochemistry. But just a few words about her. She did her PhD in a Kotutel supervision system framework with Eötvös Loránd University and Macquarie University back in 2018. Since then, she is a very important member of the Landelet research group, where our PI is István Kovács, and we have our youngest member of the seminar here, who is very cute, of course, and wants to learn a lot, right? Okay, so please, Nori.
Okay, thank you, Marty, and I'm also grateful for the opportunity. So I'm going to talk about some constraints on the depth of the lithosphere-asthenosphere boundary in the Carpathian-Pannonian region with the use of a combination of different approaches from petrological and seismological data. We are working together on this project with Dániel Kalmár and István Kovács, And actually, these data that I'm going to present, these results are quite fresh. So don't be surprised if you see that some interpretations are not yet set in stone, so to say. Yeah, so I'm going to touch on the subject of what we mean by the lithosphere-asthenosphere boundary and how it is in the Carpathian-Pannonian region. And then I will show our approach and a detailed introduction to our methods. Then there I will show how we tested some parameters and then show the results on the LAB depths for several locations. So the framework of this whole project is the Lendület Pannon Lithoscope project, as Marti already said, led by István, which has three main areas of research. It's petrology and geochemistry, seismology, and electrical conductivity and resistivity in the mantle. And the main focuses are to characterize processes in the lithosphere-asthenosphere system, especially around the lithosphere-asthenosphere boundary, to constrain the depth of the LAB in the Carpathian-Pannonian region as accurately as possible, and doing this with the combination of these different geophysical and geological approaches. Now in this talk, I'm going to show a combination of petrological and seismological results. Okay, so how do we define the LAB? What definitions are there? Well, the answer is that there are many definitions depending on what point of view we are looking at it or what parameters we are looking at. Basically, everybody agrees that the lithosphere-asthenosphere boundary separates the upper rigid conductive part of the mantle, the lithosphere, from the convective, less viscous lower part, the asthenosphere, and this allows the process that we know as plate tectonics. There's also a general agreement that the base of the thermal lithosphere is where the conductive geotherm, the extension of the conductive geotherm intersects the mantle adiabat. Yeah, this is around 120 kilometer depth, but we can see that some geophysical properties such as wave velocity, seismic wave velocity and resistivity show decrease at shallower depths already, around 90 kilometer depth, which can be considered as the base of the conductive lithosphere. But this change in these physical properties continue in, so it's not a sharp boundary, they continue to change in a depth zone. And we also need to mention the paradoxosphere concept, which was very recently developed by our group, again led by István, but it's based on the earlier theories of Dave Green, who emphasized the role of pergosite, which is an amphibole in the mantle, and although it is present in a low model abundance, it has a significance because it contains water in its chemical formula, as opposed to the other mantle model minerals, which are nominally anhydrous. And also pergosite has a stability in within mantle conditions, which has an upper limit of around here it is, around 1050 and 1100 degrees. So at this depth, which corresponds roughly to this 90 kilometers, we can expect at any minor change in temperature will cause breakdown of pergosite, melting, or crystallization. And this horizon in the mantle can be considered as the lithosphere-asthenosphere boundary in areas which have higher heat flow, such as oceanic lithosphere or very thin continental lithospheres, such as extensional basins. And in areas with lower heat flow, such as thick continental lithospheres like cratons, this is identified as the mid-lithospheric discontinuity, which can be detected worldwide. So for the Carpathian-Pannonian region, there are several maps existing that try to give a distribution of the depth of the LAB. Again, depending on what method we use, what parameters that we are looking at, we can have very different results. For example, there are the maps based on celebration sections, which show very sharp increase of the LAB depth towards the borders of the basin. Or we have the map by Bielik et al., who puts the LAB depth even in the central part of the Pannonian Basin at 80 kilometers depth. So we can say that for the Pannonian Basin, probably the most reliable one is the one which is based on the work of Gábor Tari and Frank Horváth. And also, an even more recent results, as Dani already showed his map, prepared with 1D migration with the ISP 91 model. This is, yes, as Dani already mentioned, it's not strictly a LAB map, it's a negative phase depth map. But the issue with this is that the ISP 91 model is a global velocity model, which, well, if we zoom in that a little bit, you can see how it uses a general velocity model, but the question arises how reliable or how applicable it is for the Carpathian-Pannonian region, because, for example, it uses the same MOHO depth around, I don't know, 35 kilometers, and we see no indication for a change around the LAB within this depth frame that we would be interested in. So our goals with this study were to try to see if we can create location-specific velocity profiles and apply them for the different seismic, for the locations of the seismic stations in Hungary, and to see we can constrain the LAB depth, or to see how was the significance or the amount of the partial melt, small amount of partial melt that we expect below the LAB, and actually see what the resolution would allow us to do. So we are doing this by constructing seismic forward models. This means that we first build a lithology column or lithology columns and then calculate P and S wave velocities for as many seismic stations as we can, and then use these velocity profiles for these 1D migrations on the receiver functions to calculate an absolute LAB depth. So here's a map of the seismic Hungarian National Seismological Network, which shows the permanent stations in red and I think the rest in blue are now part of the Adria array. Okay, so going on with the methods, we did the lithology column building by first making up a crust composition, because the crust makes up a relatively small part of this lithology column, but in fact it has a quite complex composition. We just took a general compositional model of Christensen and Mooney, which is actually it's a generally applicable model going from granitic gneiss composition to the garnet granulite around the base of the crust. And we also need to know the depth of the MOHO. We know that also from the recent results of Dani that he just showed a couple of minutes ago. And we need some other parameters to be able to build these columns, such as the TP curve, the model composition of the mantle. If we take into account the pergasosphere concept, then we have to examine the role of the pergosite, the amount of pergosite, and the amount of melt at the LAB. And of course, we need to have already a preconception of the depth of the lithosphere-asthenosphere boundary. I will later on go into more detail regarding these parameters in the parameter test section. But first, I would just like to show that once we have these lithological columns, we can calculate the seismic velocities with depth by using these macro Excel sheet of Ebers and Hecker, because we can just do an input for a mineral model composition for each depth section. We can put in pressure and temperature data, and then we can use these to calculate VP and VS. But it needs to be noted that this method only allows us to calculate a dry mineral assemblage. So velocities for a dry mineral assemblage, it doesn't take the amount of melt into account. Anyway, what we end up with is a velocity profile, which looks like this. We did it until 120 kilometers depth with a resolution of 5 kilometers. And then we used the S2P receiver functions, where on the x-axis there is the time, and on the y-axis there's the amplitude. And basically, during the migration, we convert the time scale to depth scale using these velocities. And then, as Daniel already mentioned, use the negative phase to calculate the LAB depth. Okay, so I'm going to move to the parameter test now. And the first parameter is the surface heat flow, which is converted to geotherms. We use the heat flow map by László Lenkei, and also the geotherms that he calculated for this paper of Kovács et al. And here are some V profiles, the velocity profiles, showing different different profiles calculated with different surface heat flow values. And basically, we can see that there is a little difference, which is not much, between the two. So between 50 and 120 milliwatt per square meter heat flows, the difference, maximum difference, which is roughly around the LAB depth, is around 4%. So it's not much, and it's really a maximum difference. We also tried to, we did a migration with the different profiles, with the different, using the different geotherms for the different heat flows. And you can see here that the higher heat flow we use, the lower is the migrated LAB depth, which is what we actually would expect. Okay, the next parameter is the model composition in the mantle. Here I put on this diagram some of the most common mantle minerals and mantle rocks. Generally, the two end members, or so to say, are forsterite and fayalite, which are magnesium olivine and iron olivine. Basically, the biggest difference is caused by iron olivine. So iron can have an effect of decreasing the seismic velocity, but its presence in the mantle is quite low. So actually, what we should be looking at realistic difference between these mantle rocks, danite, Herzbergite, Lherzolite, and actually the difference between donitic and Lherzolitic composition would be around 2.5% in the velocities. Because I was talking about the pergazite, the role of the pergazite, we also checked how an increase of the pergazite content around the LAB or above the LAB would influence the seismic velocities. And actually the results show that even if there would be an increase of 10% of pergazite, it would only cause a maximum of 1% in the seismic velocities, a 1% drop in the seismic velocities. And then last but not least, we have the effect of the small amount of partial melt, which I mentioned earlier. We cannot calculate from these Excel sheet that I used to calculate the original velocities of the lithologic column. So we used the experimental works by Chantal et al., who did who determined an experimental formulae for calculating seismic velocities with different melt amounts. They actually found that a very small amount, namely 0.1% of melt, will have no effect at all, because it means that melt is only present in the triple junctions between the grains, so they don't make up a continuous network. But here are the effects of 0.5, 1%, 1.5, 2, and 4% of melt. We can see that they have quite significant effects, especially higher melt contents can have quite significant drop in the velocities. Now, obviously, we don't really expect this much melt in the asthenosphere, but even 0.5 or 1% melt can have quite significant velocity drop. And just to compare, I put in here a model which also takes into account the effect of 10% of percosite above the LAB. And you can see that this effect is quite negligible compared to the effect of the melt drop. Okay, so here are the conclusions for the parameter test. Generally, the mantle composition does not vary a lot, so we could use, it's safe to say that we can use a general average mantle composition. We use the large-layered composition, actually. We can say that percosite content has no realistic significance. Some uncertainty may arise from heat flow, or actually not using the correct heat flow or geotherm, but the most dominant factor is the small amount of partial melt. And a question can arise, how much melt is there actually, or is there any variation in the melt content within the different, among the different stations or locations. And also another factor, which I mentioned earlier, that we need to know the depth of the LAB previously. So we need to know, we need to have an idea of the LAB depth already for the construction of the forward model. So because of this, we prepared model sets with these two parameters varying. One of the parameters was the melt content, for which we use these melt contents between 0.5 and 4%. And the other is the model LAB depth. And for this, we looked at these two maps together to determine a range for each stations where the depth of the LAB could be there realistically, and then did the models with a depth of 5 kilometers. So we did these model sets for 4 chosen stations in the first round. These are Piszkéstető, Egyházas-Kesző, Móregy, and Létavértes. And the aspects of choosing these stations were to have stations that represent different tectonic environments, different microplates, different surface heat flow, and last but not least, they were supposed to have nice, good SRF data. So here are the summary of results for Piszkéstető. I'm going to show these 2 diagrams for each of the 4 stations. On the left side, this diagram shows the amount of melt and the migrated LAB depth, depending on what was the modeled LAB depth. And on the right side, we compare the model LAB depth with the migrated LAB depth, depending on the melt content. So basically, these are the same data, but from a little bit different aspect. And just to clarify things, I'm going to call model LAB depth is what we used for an input in the models, and the migrated LAB depth is what we received as a result. Okay, so generally, what we can see here is that the lower we have the modeled LAB depth, the more the melt has an effect. So the more the melt content will lower the migrated LAB depth. And also on the right side, you can see that these different melt curves seem to show a bit of a decoupling towards lower modeled LAB depth, and towards higher modeled LAB depths, they are going towards 1 point, or in this case, there's an inflection point. Okay, and compared to this, this is the other station at Hazards, where the modeled LAB range, actually the LABs on the map of Tari and Kalmár were quite different. So we did a modeled LAB range, which was a bit wider. And we can see here that these melt curves are now going into 1 point, and then there is no change in the migrated LAB depth once we are above 75 kilometers for the model LAB depth. And this is because this model LAB depth is probably beyond the depth for the chosen LAB value on the receiver function. So we can safely say that this is likely a maximum LAB depth for this station. And if we look at the curves which represent the modeled LAB depth, we can see that this is why the one at when we assumed an LAB depth of 75 kilometers, then this curve is quite flat and there's no change. We see similar things in the diagrams of the Nóra station. In the modeled LAB depths were between 45 and 75 kilometers, but then again at 75 kilometers there is a maximum where above which there is no change in the melt content. There's no change no matter how we vary the melt content. And finally, Lithospheric, which is, Dani already mentioned, it's on the Great Hungarian Plain. The lithosphere is considered quite thin here, so we did our models between 35 and 55. And again, it looks like that 55 kilometers is a maximum because that's where these melt curves meet. Okay, so here are the conclusions for these results concerning the modeled and migrated LAB depths. So generally, the migrated LAB depths were always usually greater than the modeled LAB depths. This actually is a question why that could be, but we can say that at lower modeled LAB depths, the migrated LAB depths varies more with the melt contents, but there can be a maximum value pinpointed for the LAB, above which there is no change. So the changing melt content will have no effect. And if we use a specific model LAB depth, then the increasing melt content will decrease the migrated LAB depth, except above the maximum where it will just be flat. And then, so what are our plans for the future is that we're going to continue building these models for the rest of the stations in Hungary and see what results they can give us. We will try to see what if there is any difference between or regarding their location, their tectonic environment, or in any aspect, and also try to see if the melt content, if we can see some variation in the melt content. So as you have really seen, this is a work in progress. So any constructive comments are very welcome, and thank you for your attention.
Thank you, Nori, for introducing us the beauty and challenges of LAB determination. So if any from the audience has a question, then please raise their hand. If not, then I would have one. It might be a stupid question, but I was wondering when you introduced the effect of the minerals on the seismic velocities, I was just wondering how distributed this mineral can be. Like, for example, the pergazite, does it count? Or for the mineral at the grain melt at the grain boundaries, does it count for the seismic velocities, whether it is presenting as a layer, you know, in a block, or whether it is presenting distributed or dispersed in the rock? I mean, does it reflect it on the seismic velocities?
Good question. So I prepared these models just by considering that they have like a general normal distribution. I could make models where, for example, I assume a layer of, say, pyroxenes. I haven't done that, but actually it would be interesting to see. It's not impossible to see to make a model like that.
At this textural point of view can make some effects.
It could, or yeah, it could just for like one depth. If it's some layers, for example, could have an effect for that layer, which would appear in the profile as a change in the seismic velocity. Yeah.
Thank you. Any other question? So I'm checking the online participants. Or I'm asking Gabor whether do you see anybody raising their hands? If not, then thank you, Nori, for this nice presentation. And last but not least, I don't think everyone needs to introduce our last speaker, but nevertheless, I'm doing it. So the next speaker will be István Kovács, the head of the Lithosphere Physics unit and the PI of two prestigious projects, the Pannonian Land project and the Topo Transylvania project, and also the vice director of the institute. So please, István, give your presentation about the beauty of the asthenosphere.
Thank you very much, Marty, for the kind words. So again, I'm in a position that I'm standing between the, let's say, the real fluid session and the rock science. So this talk will be more like of general nature, and also to give you some insight that you shouldn't underestimate the deep side of the force. And I just would like to tell you a story with Sierd Cloetingh when we drafted the paper together with Nori on SKS splitting and the role of the asthenosphere. And after Sierd having read the manuscript, she came to me with a face like, I knew exactly what it meant. And Sierd told me that, István, geez, you just forgot about the lithosphere in the story. So eventually, we also included very nicely, using Sierd earlier results, the lithospheric part as well. So in the talk, it just, forgive me, it's probably my personal attachment to the asthenosphere that I will focus on this part of the Earth's interior. But of course, I will never forget about the importance of the lithosphere and the rest of the upper mantle. So I just trying to tell you how important the asthenosphere is, and it probably does have a contribution to the global processes that we see and we call plate tectonics. Okay, so let's start the talk with a very recent summary figure, because we need to ask the question, and this is on the fundamental question, that what is the asthenosphere? And probably it turned out from Nori's talk that it's not easy to define, and if you are a geophysicist or if you are a geochemist, you may give different answers to the same question, and it's not a problem. this is how geoscience is. But I just would like to tell you that there is a kind of emerging data and also agreement that we do have a partially molten layer of the upper mantle beneath the lithosphere and the bottom of the, let's say, as they call it, the low velocity zone. So basically, generally speaking, the asthenosphere is a relatively thin layer of the upper mantle between the lithosphere-asthenosphere boundary and the bottom of the low velocity zone. And if we would like to define what the asthenosphere is, there is a also growing number of observations that this is a peridotic material predominantly with very low degree of partial melt. And when I say low degree, it means around 1% of water or melt, or even less than that. So it's a very tiny amount of melt, but it plays a crucial role to make a rheological viscosity difference and also supporting plate tectonism. So the first take-home message is that probably the asthenosphere is a relatively thin, partially molten layer on the top of the upper mantle, which supports the tectonic movements. Okay, so if we move on, of course, the second obvious question that, okay, you say that it's partially molten, but what's the reason for this partially molten state? And I must tell you that, again, even decades after the birth of the modern plate tectonic theory, there are still very fiery debates about whether the upper mantle can be in partially molten state at depth corresponding to the asthenosphere. So what I'm telling you is my personal view or interpretation, and I will highlight the other ideas. So I think the main reason for the presence of partial melt, it is simple, because we have very tiny amount of volatiles in the upper mantle, like Marty pointed out, not only water, but carbon dioxide and other species. And you don't need much of these components, of these fluid components, to suppress dramatically the solidus temperature. So you need only a few hundreds of ppm to do that. And if we accept that such low volatile content can suppress the solidus, we have a partially molten upper mantle somewhere between 100 kilometer and 250, sometimes maybe 150, sometimes maybe up to 200. So the reason for the presence of partial melt is that water saturated or volatile saturated solidus. But as I told you, there are contrasting views, and we also must give credit to these ideas. So one explain the presence of the asthenosphere simple by grain size variation, namely that the grain size in the asthenosphere is smaller than in the overlying lithosphere. The other idea is that we have changing redox conditions in the upper mantle, and this can also create a transition. And this more or less coincides with the place of the with the position of the asthenosphere. Also, it's a very popular idea of the MIT, Karato and his school, proposing that we have this elastically accommodated grain boundary sliding, which means that at a certain temperature and pressure, there is a weakening at the grain boundaries, and this causes this more plastic behavior of the asthenosphere. But again, you don't have to assume the presence of partial melt. And also there is maybe a fifth or sixth, or I don't know, a lot of competing theories proposing that we have a change in the anisotropy, and that causes all the observation that we have of the asthenosphere boundary. So again, the take-home message is that there is still a lot to do in experimental petrology and also in geophysics to understand what the lithosphere-asthenosphere boundary is. And in the previous talk, Nóri did a great job to demonstrate how complicated it is. And we are still uncertain whether we are actually beyond the resolving capacity of the receiver function to be able to answer this question. So the question may be that the receiver functional analysis itself is not easy or not enough to resolve this question, what we are posing. So again, it's a open and complicated thing. So don't take anyone seriously saying that we know what the lithosphere-asthenosphere boundary is. Okay, and now I just would like to highlight a few case stories or geological, let's say, interpretations about the asthenosphere. And of course, our playground is one and mighty Carpathian-Pannonian region, which is an excellent test bed because it's geologically young and it preserved a lot of processes of let's say, the past 10 millions of years. And this is a cartoon from Frank Horvath's landmark paper. Frank played a key role in the geodynamics of the Carpathian-Pannonian region. So I always very positive that a lot of people remember him because I think he deeply deserved that. And if we move on and we try to list previous theories regarding the asthenosphere, in Frank, classic adaptation was that the Pannonian basin, the extrusion and the extension, of course, was driven by the subduction rollback. And the subduction rollback was mainly responsible for these processes. And also in his model, the asthenosphere in the early model just played a passive role. So it was sucked into the Carpathian embayment by the rolling back slab. So this was the first, let's say, idea about this. After that, Frank a little bit moved on, and later on with Patzena, he came up another model a little bit more than a decade ago, saying that we have the inflow of the asthenospheric material through the dynamic slab. And this comes into the Carpathian embayment and then move towards the rolling back slab. And if we would like to a little bit zoom out and see that on a regional scale, then the driving force in the model was the rolling back dynamic and also the slab at the openings. And this pushes out the asthenosphere and it basically comes into the Carpathian embayment. So in this model, the asthenosphere has a different role, and I would like to call your attention to this fact. So in that case, it's not just the passive movement driven by the rolling back slab, but actually it drives both the extrusion and also it navigates or enhances the slab rollback. So in that particular model, the asthenospheric flow or the asthenosphere itself plays a different role. And we also proposed a model more than 10 years ago, and we largely built on the classic models of Martin Flower and others for Southeastern Asia, where they proposed that the collision in the Himalaya with Asia, between India and Asia, just pushed the asthenospheric material out, and it had a serious impact on Southeastern Asia, which is reflected in the movement of tectonic blocks and also in volcanism. So we also proposed originally that the collision in the Alps might have played a key role in driven the asthenospheric material out of the collision zone, and may have been responsible for opening both the Pannonian basin and also the Mediterranean here. And again, the main point is that this asthenospheric flow is not a passive flow, it's an active flow, and it drives from below most of the geodynamic processes. At the same time, I also have to admit that this model suffers from some space and time problems, because how we consider in that model the collision in the Alps. So from what time do we consider the collision, and how exactly the squeezing of the asthenosphere out of this collision zone happened? That's a great question. It would need probably further modeling. Okay, so in the past few slides, I just trying to highlight that the asthenosphere can have a different role in the formation of the Pannonian Basin, and we can really look at this story from different angles from below. And now I just turned to the more recent, let's say, asthenospheric business beneath the Carpathian-Pannonian region. This is the SKS data and some papers from the past few years. Basically, the shear wave splitting is an excellent seismological tool to monitor the texture of the asthenosphere or the upper mantle beneath a given region. And if we combine these directions and also the strength of the SKS splitting with xenolith or upper mantle xenolith based data, then we can basically highlight and understand how the upper mantle looks like from a textural point of view beneath a particular region, and also what kind of asthenospheric deformation or asthenospheric flow we might expect. And also, of course, it images the present day state of the asthenosphere. So we cannot really say more about the past. And the question almost always arises, okay, these stories are nice, but how can you basically date the processes what you are observing in upper mantle xenoliths, and how long they preserve the deformation or the geodynamic history? And the answer is not straightforward, but certainly as we are going deeper with the increasing temperature, then the deformation memory or the geodynamic memory of materials becomes shorter and shorter. When we reach a certain point, then in geological terms, it's almost instantaneous. So that needs not much time. But of course, as we are approaching the lithospheric mantle or even the crust, the story is different. The lithospheric mantle and the crust may preserve much longer tectonic memories going back to millions, maybe hundreds of million years without any problem. So that's a key difference when we are looking the geodynamic processes and also plate tectonics from below, because it can provide us only with a very, very recent snapshot what's going on in the region. Okay, and cutting a long story very short, because Nóri has given already a lot of talks, luckily in the past few months. I just try to summarize her main results from a very recent paper. So what we think that the SKS data tell us, and it's of course it's an interpretation, that basically we observed a two-layered structure in the central part of the basin, where we think that the shallower and very thin part is the old and preserved lithospheric mantle. And the yellowish part is the so-called, let's say, juvenile or new lithosphere, which was added to the bottom of the lithosphere after the extension and extrusion of this lithospheric box. Because during the thermal relaxation, there is a process when the partially molten asthenosphere transforms into the solid state, and from rheological point of view becomes part of the lithosphere. Okay, so that stands for the central part, and we think that during the extension and the extrusion, there should have been, or it's logical to assume, again, as I told you before, we don't have a snapshot back to the Miocene, but what we can assume, and it's logical to assume, that we may have this horizontal foliation and horizontal lineation in the lithosphere, because the asthenosphere, regardless whether it was a passive or an active flow, it must have flown mainly in horizontal direction into the basin. Okay, and the story, and of course at the edges of the Pannonian Basin, we couldn't really observe this, let's say, dichotomy of the lithosphere, because we had only one layer, and also in the xenolith record we didn't observe different material properties with the changing temperature. So we can assume that in that marginal areas where the lithosphere is also much thinner or thicker, sorry, we didn't observe that difference. And the other important thing, which is in here, that we made a modeling and a calculation whether these SKS data, how can we interpret in terms of the xenolith EBHD data and lattice preferred orientation. And the most probable solution is that we have a vertical foliation in the asthenosphere. So we just move, okay, no, I just come back. So we have this vertical foliation in the asthenosphere. This is for the present day asthenosphere beneath the region. And the lineation is horizontal. And we think that this is perpendicular to the present day convergence between the Adriatic indenture and the Trans-European suture zone. And very early on, when 10 years ago we published first results on the SKS data, we thought that, well, the story is relatively easy. We have the Adriatic indenture, we have the stable Europe, and then we have a kind of, let's say, trap for the asthenospheric dome when it's under compression. Now we think the story is a little bit more complicated and more regional, because the Trans-European suture zone is a very important tectonic barrier on the east. Its thickness is almost 200 kilometers. So you can imagine easily, if you have any asthenospheric flow, which has a component towards the European plate, it will be just simply taken up by the European plate itself, and it will automatically create such kind of texture in the asthenosphere. And this is exactly what we see if you look at these images. So as we are approaching towards the Trans-European suture zone, most of the directions, regardless where we are, start to mimic the direction of the Trans-European suture zone. But still, we can say that there is a, let's say, a constant suffering for the asthenosphere beneath the Pannonian basin, because it's still under this compression, which I was talking about. And actually, this work was published more than 10 years ago. And that time, the result that the Polish colleague found during the processing of the celebration data was quite surprising for a lot of people. And it, of course, sparked really big debates, because what we observe is a celebration 5 profile, which goes from the Pannonian basin to the Eastern European craton. And what you observe is it looks quite good on the crustal scale, because that's the usual story. Of course, we have the subduction of the European plate underneath the Pannonian basin. It's all fine, but if we go deeper, we find something which, let's say, doesn't really fit into the common wisdom or the image that we have about the Pannonian basin, because it seems that the Polish colleagues found reflectors which are actually dipping or diving under the European platform. So it seems as if the upper mantle or the asthenosphere is just going under the orogenic rim. And that time, I think that there was no people who could understand that or comprehend that. And you know, not a long time ago, they created another section. It goes from the Apuseni Mountains to the Ukrainian Shield, also by Polish colleagues. And you know, the story quite the same. We have in the crust and in the shallower levels the same story, which fits very nicely into the geological record. However, if we go deeper into the upper mantle, we start observing again strange reflectors, which going under the Eastern European cratons. So you might ask the simple question: what the hell is going on here? So what is the driving force for these processes? And you know, just to puzzle you even further, I just show you some cross sections going from the Carpathian basin to the Bohemian plate or the Bohemian promontory. And what you see on both sections, and I just would like to call your attention to this detail of this section that we have the Pannonian Klippenbelt, which is thought as the suture zone between Europe and of course the southern tectonic plates. However, if we look at the Moho in deeper levels, then we see a clear offset between the surface manifestation of the tectonic boundary and the tectonic boundary in the deep. And it's clear only in this part of the Pannonian Klippenbelt. So if we move into this direction, we see mostly that the Moho is nicely below the Pannonian Klippenbelt. So the question arises, what can be the reason why in that particular place, the Moho is tens of kilometers offset from the Pannonian Klippenbelt. And if we move to another part of the Pannonian Basin, is the Vrancsa slab. In the Vrancsa slab, we observe something also very similar. So we have the suture zone here on the surface, and you see that the seismogenic body is again kilometers away from the suture zone on the surface. So again, I just have to ask the provocative question that what the hell is the explanation for this? Also for the reflectors going under the orogenic rim towards the stable platform. And this offset that we observe, just go back a few slides. Yeah, we observe this offset only here in the southeastern part of the orogenic rim and the northwestern part of the orogenic rim. But of course, if you can tell me any place around the orogenic rim where we observe such offsets, I'm absolutely curious about that, because then we may have to think about this more. But the idea, what I would like to say, and we also propose that in this paper with Nóri, it's called the asthenospheric jam effect. So basically, the asthenosphere has to go somewhere from this collision zone. So asthenosphere must do something and must take up the deformation between the thick colliding Adriatic plate and the stable European platform. And you know, how can we resolve this place problem for the asthenosphere? It basically, you know, the only way may be up or just to escape, you know, across the orogenic rim. And why is that two particular location in the Pannonian Basin is interesting? I mean, this part here and also the Vrancsa zone, because these two regions are exactly the parts of the orogenic rim where this SKS direction is almost perpendicular to the orogenic rim. So it may well be, I'm not sure whether this is a good explanation, that the asthenosphere is simply pushed to these lithospheric blocks around the orogenic rim. And basically, this is the two directions where the compression on the asthenosphere can provide probably the best driving force or the highest strength, or not highest strength, the highest stress on the lithosphere. And the lithosphere may wants to escape in these two directions from the convergence. So yeah, it's just an idea. I'm not saying it's right. It's just something, you know, appetite for thought. So let's think about it. But I would be really curious to hear your opinion on this. Okay, and in my talk, I also promised that I will be talking about the volcanism as well, and also the gassing. This part of the story will be slightly shorter. Regarding the volcanism, of course, now I will only focus on the Pleistocene basaltic volcanism. I'm not touching much on the alkaline volcanism. It has been long a problem for the petrologists that how can we produce alkaline basalts during the tectonic inversion, because most of the alkaline basalts in the Pannonian Basin were produced around 5 million years ago, although there are some older ones in Burgenland in Austria, but mainly they are 5 million years old. And to explain that, that there was always a idea to say that, okay, we have this asthenospheric updoming or extension, and the pressure drop creates melting, and then we have alkaline basaltic volcanism. But the problem is very serious. The problem is 5 or 10 million years in time, because the volcanism, it happened much later than the extension. So therefore, we made a detailed study into the water content and volatile content of the asthenosphere beneath the region. And it became clear that the asthenosphere still probably contains a very small amount of partial melt. And the conversion or the tectonic inversion and the convergence between the European platform and the Adriatic plate was an excellent time just to squeeze the partial melt out of the asthenosphere. And it's not really difficult, since the basalt has lower viscosity, of course, and lower density than the surrounding mantle. So the only way is up. So it will move towards the surface, and it can use the deep deformation zones of the lithosphere above. And this phenomenon was already touched in several talks with Sierd and Frank Horváth's model back to 96, that we have this lithospheric scale folding. And of course, if we have folding, then we must have also some kind of deformation inside the lithosphere, which can support this melt. And also don't forget that we are in the thermal relaxation state, which means that the lithosphere gradually becomes stiffer and stiffer with time. So what we are saying here, that the asthenosphere, of course, played a very important role in the genesis of Pleistocene alkaline basalts. And the inversion helped the partial melt in the asthenosphere to come out and come to the surface. So it's not a contradiction that the basalts came to the surface during the tectonic inversion, but the tectonic inversion may have even helped the basaltic melt in this process. Okay, and the last topic, very briefly, Marty was very kind to talk a lot about carbon dioxide and its role, but you know, when we talk about climate change, we also have to talk about geological carbon dioxide emission. And if we are honest, we still really don't know how much is the carbon dioxide emanation, the geological carbon dioxide emanation, because most of the models that we are citing only considers active volcanic areas or semi-volcanic areas where you have some post-volcanic activity. But none of these models consider areas like, for example, the Pannonian Basin, where we know in a lot of locations that there are carbon dioxide emanations not related to active volcanism at all. And then the question arises, what is the source of that carbon dioxide? So how we can explain that? And it's just a possible explanation. I'm not saying that is the overall explanation, because as Marty and Thomas pointed out in his previous talks, there could be also crustal component in the story. But what we observe is always the deep upper mantle signal, the presence of this signal in these gases that we find on the surface. So it must have come from the lithospheric mantle or even below from the asthenosphere. And one possible solution and contribution to this carbon dioxide emission is just simply the cooling asthenosphere itself. So we can say that the asthenosphere is itself a mega magma chamber, because the asthenosphere contains partially molten material, as I told you, small. But if we consider the whole volume of the asthenosphere, and if we accept that there are very localized deformation zones which can all the way go to the asthenosphere, it's a reality. So what happens is, if you have a partially molten asthenosphere, like the one beneath the Pannonian Basin, and it's in the thermal relaxation stage, then it continuously crystallizes, which means that during the crystallization, the carbon dioxide is basically not the favorite element of the upper mantle, because there is nowhere to go, especially beneath the Pannonian basin, where the carbonate minerals in that depth are not stable at all. So the carbonate has only one choice, to leave the upper mantle and start its journey towards the surface, which is always driven and enhanced by the continuous deformation that's going on in the asthenosphere. So to cut a long story very short, what I would like to say that in young oceanic basins and in young extensional continental basins like the Pannonian basin, the asthenosphere itself can be the source of carbon dioxide. Again, I'm not saying that this is the only source, but certainly if you don't have anything else, so if you don't have decomposing carbonatitic rocks in the crust or whatever, then it can be a reason. And of course, if you just focus and channelize this carbon dioxide into this very localized deformation zone, you can extract a significant amount of carbon dioxide from the upper mantle. Okay, so I think, yeah, it's just a model from Thomas, from his recent paper, it's just under review, showing for the Vrancia zone how we can imagine, or how can we picture this fluid origin. Of course, we have one player, the asthenosphere, as I just explained, but in the Vrancia zone, we also had another player, and it's the Vrancia seismogenic body, where probably we have dehydration and decarbonization of metasomatic materials. And these fluids then come to the surface along the Eastern Carpathians, even areas where we don't have active volcanism at all. Even in the past, we didn't have any. So the take-home message of the talk that, and I may have focused a lot on the asthenosphere itself, but when you think about different deformations of the lithosphere and geodynamics, don't forget the asthenosphere, nor from geodynamic point of view and nor from geochemical point of view, because it can be a key player in magma genesis and also as a source of volatiles. And just at the end of the talk, this is just a little advertisement, but it's related to the topic. Sierd Cloetingh, Kristóf, who is in here, and of course Sierd, and myself is editing a special volume for Acta Geodetica and Geophysica, and the title is Crustal and Upper Mantle Structures and Processes in the Alpine-Carpathian-Pannonian System, Recent Advances. And I also want to call the attention of the online participants that the submission is open until autumn this year, and we are expecting novel contributions in the topic which I just highlighted. So yeah, it would be great if you can contribute to this special volume. And yeah, thank you for your attention.
Thank you very much, István. Very nice presentation. And I pass the microphone to Kristóf.
Thank you. So I had a question regarding the SKS data. It's partly related to my ignorance in the topic. So you interpreted SKS direction as basically the strike of the main foliation, like in the asthenosphere, right? But what else can play a role in defining an SKS direction? So what defines really the SKS? It can only be an orientation of the material, or can it also be related to the stress field itself? Can the stress field itself modify this or not?
Oh, yeah. Oh, thank you for the question. So the two things are absolutely related, and it's pretty much goes back to the fact I mentioned that in the asthenosphere, the recrystallization is almost instantaneous. So the asthenosphere has the capacity to immediately take up the stress field and also to recrystallize. And what we know from the literature, that this direction that we see is always related to the anisotropy of mineral so-called olivine in the upper mantle. And basically, the elongation of the olivine fast axis defines the SKS direction. So it's pretty much related always to the stress field, because the olivine will grow perpendicular to the stress. And how we actually interpreted this vertical foliation is, again, goes back to the Senolyth record, because Nóri considered 5 different scenarios. So we also assume that we have horizontal foliation. We also assume that we have oblique foliation and then vertical foliation. And the strange thing was that for the horizontal foliation and the oblique foliation, we got always extremely thick layers from the anisotropy, which is very much thicker than the low velocity zone itself. So we, of course, one can say that, okay, it's still a possible scenario, but very unlikely, because most of the anisotropy is concentrated in that low velocity zone, and probably it's also not homogeneous. So it may be stronger close to the base of the lithosphere, and it gets weaker with the depth. But again, it was unrealistically thick. So that's why we say that the 100, 200 kilometers we got agrees very well with the thickness of the low velocity zone.
Right, thank you. So basically, if it grows perpendicular to the SH max direction, let's say, then however deep that is, it still fits quite well to the actual stress data that we have from the crust. So that's quite interesting.
And also there is one thing I didn't mention, that probably if we have still melt in the asthenosphere, then the melt also will be concentrated along these vertical zones. So we just have it with Tibor and Attila modeling on MT, and we have data suggesting that it's not only the LPO in the minerals which has this anisotropy, but also we do see a very stark, profound anisotropy in the conductivity of the asthenosphere as well, but very high contrast. And I think the only way how you can achieve that, if you have this vertical foliation and probably some partial melt aligned along these zones.
Thanks.
István, I'm going to be the difficult customer at the end of the day. If you go back to your cartoon, like a couple of slides back, when you show this lamella, this model of yours. Oh no, this is fancy. The other way.
Sorry.
I tell you, this one. The part I don't get is that, we all like this idea of the lithospheric scale folding. Sierd wrote this to us, and I really like it. This works just fine. It's easy to comprehend. I can perhaps understand the squeezing of the whole story from north east to southwest, and the foliation or lamination or whatever you want to put in the asthenosphere. But what I don't get is that you start to talk about deep folds, which would kind of conduct this melt through this lithospheric scale folding. You don't need to have fold. I think this is a overstatement when you say that, okay, you have folding, and then you have to have big crustal scale deep folds. We don't see the evidence for that, in my view. And the other observation is that if I look at the map and if I see these alkali basalts, they are all over the place without any kind of order to them. Whereas the only statement we could make, or I can make, is that they tend to be around the perimeter of the Pannonian Basin, but other than that is broken glass. There's no geometric order to them, not even in a very first order manner. So I see this as a weak point in this particular cartoon, the way you pitch the story. The other elements are okay, I can live with it, but where's the evidence for this deep fold? And do you have to have deep?
Yeah, I mean, the evidence is that we have the alkaline basalts on the surface, so they must use some deformation zones to come to the surface. So I think we need to explain somehow that we have these alkaline basalts. Oh, well, I'm not sure that we need to have that, but I would hardly, I mean, imagine that, okay, we have alkaline basalts without having some kind of, let's say, organized conduits in the crust and in the lithospheric mantle. Because, and just coming back to your point, actually, we did some preliminary research on the position of the alkaline basaltic domes or alkaline basaltic localities in Nógrád-gömör, the Bakony-Balaton Highland, Styrian Basin. And there were two directions which seemed to be, let's say, sticking out. One was this northwest southeast, and the other one was the perpendicular one, which is more or less parallel with the mid-Hungarian zone. And we also used geomagnetic data on that to consider those volcanic edifices which are not on the surface. But again, I think that that's one story that we need to understand together. I mean, I'm not a structural geologist and I don't have experience with the crust like you do. But for me, as a petrologist, something is needed which facilitates the way of these melts to the surface. And also inside the basin, we also have basalts, like in your talk, in the Békés Basin, we also had those, let's say, anomalies which could be alkaline basalts. And also not only there, but in the Nyírség and Derecske Basin, I also remember talks in the Formelelgi, where they identified similar things close to the basement. So I think probably the spread and occurrence of alkaline basaltic rocks may be more widespread in the Pannonian Basin than we thought. Just we simply don't see them because it's covered by sediment.
Again, challenge is that you don't need to have holes which kind of follow this model that you show. And just like the salt comes through stuff, and then people for all this time didn't get it, why and how and things like that. That you can have not only one that is going through the
Yeah. I mean,
without creating this model,
so actually, we Sierd suggested in this model that we should include this kind of salt tectonic model, that indeed the asthenosphere and the melt can indeed behave that way. So I mean, you know, you are absolutely right. So it may have been an overstatement to say that it's deformation zone, but for me, again, as a petrologist, it was hard to comprehend how we can bring that to the surface. But your model was it may be an alternative way to bring that. Yeah.
Just I can comment this exactly. I agree with Gabor that you do not need this through going for. Okay, this is the melt will come up. If there is a buoyancy, this will do without any hesitation. I guess even some they reach the surface, so they do not need any help or guide or something. The other thing is that in the at least in the upper middle crust or even the lower crust, we have low angle structures in general. Okay, so then to create subvertical features, it's difficult, and even more subvertical features will not take up any shortening. Okay, you cannot take up shortening with subvertical features. Okay, so they are already not related to the folding. Okay, this is very clear. In that case, there should be some old inherited stark slip folds, but even they do not go below the lower crust. They reflect them down in the lower crust. Okay, so this is just comment. I just emphasize what Gabor said, that maybe this part can be reconsidered. Now you mentioned once there are several things which will create a lot of discussion between us, I think, but maybe there's no time for that. Just I reflect one of the things you stated about the branchia zone. Okay, you said maybe you can go to this figure when you said that, okay, the suture is not exactly where the actual plate is located. But in fact, this is what we see everywhere. So I do not understand what is the surprising for you in that figure.
But, sorry, Lottie, what did you?
But what is surprising that if you go to the dinarites, you have exactly the same. You have the suture in the Sava, more or less we agree on that, and we have the present day undergoing slab is beneath the Adriatic coast. There are 200 kilometers shift between the two. So if you want an example, this is one thing already. You asked me if you asked us if can say to you an example. So this, if you go to the Alps, the suture is horizontal and the slab is vertical. So this is, for me, this is the normal way of life, how we do see it. We have a suture, and the present day slab is a completely different geometry. Yeah, the LN is 600 kilometers from the suture. So maybe you wanted to express in other things, but what you asked for as a question, we can provide you such situation that the suture and the slab is
okay,
Maybe you wanted to express something different. I don't know.
Yeah, because it's okay. Of course, it's a different story when you have this, like in the dinarize, this delamination thing, when you are no longer under the suture zone, but it's going backwards. But still, the big question is, we always have to ask is, okay, but what is the driving force, which very often make these slabs vertical, and even at some places the brancha is not it's actually almost tilting towards the Mosian platform. So
overturned slab is known in the world. So this is not a surprise that you have overturned slab.
But you need something, a process which basically drives this delamination.
Yeah, this is
and the thing I'm saying that because the common assumption is that, okay, this is gravity which drives the thing, but the problem is, if we assume that the delaminating slab is not oceanic, then we have a serious problem, because the lithospheric plate and then the lower lithosphere is not there's no large density difference with respect to the asthenosphere. So it's possible, of course, when you have oceanic plate and you have eclogites, which provides the density contrast. But in other cases, you always need an excess driving force. So the thing I think about the region is that the asthenosphere can be such driving force even for the present geodynamics.
No, it's perfect.
Yeah,
this is not
but thanks.
It is not a doubt that this is an observational feature that we see that in the right and upper crust, fantastic fold and suspect, and you have a completely detached mental lithosphere beneath, and back. Okay, I stop.
Yeah, it's just one comment on, because this deformation zone thing is very important, because we have, not only here in the Pannonian Basin, but elsewhere, these carbon dioxide emanations, which are focused along fault zones. So this carbon dioxide, we know it comes from the upper mantle or from very deep. Then the question is still there, that how is that possible? So I think that's something that we have to think about together, because it clearly must come through some porosity contrast. So that must be something which drives up from the deep. And then when I say deep, I'm not talking about 10 or 20 kilometers. It may be much deeper than that.
Maybe I can comment this, that probably we see the things from the completely upside down.
Yeah, that's sure.
The upper crust, anything which is coming. This could be magma, gas, or liquid. This could be a concentration upper crust. Doesn't matter. It was completely homogeneous in the lower crust. This will be concentrated in upper crust. And I'll tell you very easily why. Because the upper crust is much more anisotropic than anything else. Because there you have absolutely looking for the porosity point. for example. Okay, so you have oriented porosity guidance in the upper test.
Yeah,
This is the reason that on the surface we will always see something anisotropic along this zone, because when water arrives at the base of the upper test, this will be guided along porosity zones. Okay, so this is perfect. We have
yeah, but the thing is, the question is still not answered, because yeah, that's the easy part to explain, because we know that. The tricky part to explain is what happens in the lower crust and the lithospheric mantle. So that's the hard part of the story. So how we can bring up those gas and matte from the asthenosphere.
Absolutely, just simply I say
Yeah.
we are not get an homogeneous distribution of anything which is coming out across the upper.
Yeah, I think that's clear. It's obvious. I mean, the question is that to bring there.
Point of view that in my view it's important. But okay, then more because we agree that this is important.
And also the lithospheric mantle. Yeah.
Yeah, it's even.
Okay, it's nice to see the
unfolding
seminar is.
discussion.
This is how it is.
Yeah, that's nice.
Absolutely.
But I think we can continue later on with
Yeah.
some refreshments, along with some refreshments, if you don't mind. Only if anybody else has a last question, but if not, then I think this is the
Also
time for
wish.
announcements.
Yeah.
Can I pass that?
Yeah, probably Sierd has a.
I know Sierd has an announcement to make. If there's anything else.
No, from my side, I just would like to ask or thanks the online participants for the attention, and I just asked Csongor if we received any question through the chat window. We should check that, because I don't want to let the people alone. So yeah, thanks again, and please don't go away, because Sierd Cloetingh has an important announcement for us to this autumn.
Well, very, very brief, because I don't want to stand in between you and the fluids that have been announced. And well, first of all, I think you will all agree with me that this has been a most inspiring day. And I think a big thank you to István and his team here in Chopron. So please give him and them a hand. As I told you, of course, we look forward to further lively discussion, of course, accompanied by some fluids. We all know after Marta that fluids are in the essence, and especially if they are combined with some solid earth science. In that context, the topic of coupled deep earth and surface processes, I think we has kept us off the streets today, and it's not over yet, because the issue of coupled deep earth and surface processes happens also to be the topic of Topo Europe, the pan-European platform of the International Lithosphere program, basically bringing together the European solid earth community already quite a few years, and very soon the new science plan for Topo Europe will appear as an invited review paper of the international journal Global and Planetary Change. And I'm very happy to announce that our colleagues here in Chopron are willing to host the next Topo Europe meeting here in the last week of September, the week of 25 September, with an arrival here in Chopron on 27 September, a meeting on 28 and 29 September, also to proceed with the generation of new research proposals to be submitted to different funding agencies. And of course, last but not least, to have a field trip guided by Kavatari and Christoph Korkolov. And I can assure you also from previous experience, that's always a highlight. And the further information on this will be posted to you. but we would like to basically to stress here that we will be very happy if you would keep these dates on your radar. And we count on you also to make that meeting, at least make an attempt at the meeting to make it at least as lively as the meeting we had today. So that's it. And again, a big thank you, István. And you're still alive and you're mentally prepared for the next meeting. Okay, keep going.
Thanks, Sierd, and thank you very much for distinguished guests for coming. We really had a great day and a lovely discussion, and I hope that we will continue also the fluid session and also the meeting in September in the same spirit. So yeah, thanks again for the attendance. I hope you enjoyed it, and I also say goodbye with the online participants. So yeah, have a nice evening. Goodbye. Fair.